introducing, but I went at such a clip last time, I don't think any of it's got in. So I'm just going to start without people who are late. This is, you'll be distraught to know, the last lecture that you'll get from me, which doesn't mean you shouldn't turn up on Tuesday, because Neil will be here to talk about digital stuff and horrible things like that. We don't like any of that at all. Actually, if you bother to have a look at the thing about EDSAC that I sent round and put up in the start of the last lecture, that's all digital circuits, but maybe valves, and you have to worry about the sort of things we're discussing now, even if you just want ones and zeros, because the valves are pretty awful in terms of their characteristics. By comparison to a nice MOSFET made in the CMOS process. Anyway, what we need to talk about right now is to finish off the discussion of noise. There should be just one set of notes going round. You'll be pleased to know that there's much more chance of this turning up on the exam than the other bit. So if you're going to bother to pay attention, today's the day to do it. We will talk briefly about an equivalent circuit for noise at low frequencies. That's to say, different from the stuff we were discussing on Tuesday, where I was talking about noise factor and impedance match systems and all that sort of thing. Now we're back in the volts and amps and the standard op-amp circuits that we're used to. And we'll have to talk about how we can use some noise generators to model the system. So we'll quantify the noise generators. And then I'll give you a model for an op-amp. And the point of the op-amp model is to come up with some ideas as to how we can design our circuits to make them as low noise as possible. It's not to give you a big shiny model with a massive equation at the end, which you're then supposed to remember. Because that's not the point of equations. They're not supposed to be remembered, they're supposed to be derived when you need them. The point of equations is only to inform you as to what decisions you might make about your circuits. So we will take away some words that tell us how to design a low noise op-amp circuit. I'm not worried about the equation. Although I will do an example at the end, which it will probably be a good idea to pay attention to. So, noise generators. We will have in our system a very large number of noise sources. Every time we put a transistor in, we'll get at least one noise source. And every time it will be a shot noise source. Every time you put in a resistor, you'll get a thermal noise source. So if you had 6 transistors in your op-amp and another 6 resistors, say, that puts you up to 12 noise sources, which you have to work out how much effect they have at the output, and then square them all, and then add them all up, and then square root them to give you an answer. That's an unbelievably large amount of work. If you were going to do it by superposition, you'd need 12 little sub-circuits to deal with. No wonder I'm not going to ask it in the exam. It would take 3 hours. We don't want to do that. We would like to reduce, as we did for the impedance match systems, we want to reduce all of our circuit noise into 2 generators, which we put at the start, and we compare them with the signal, which is also at the start. And we do a signal to noise ratio thing like we did before. This is a standard method, that's to say you can do it for pretty much any linear circuit. It doesn't work so well for oscillators, but we define noise for oscillators in a slightly different way usually. But I'm not going to go into it now. You can read about it if you want. So being a standard approach, once you've got your 2 noise generators, the mathematics you have to do to get to what does this mean in terms of nanovolts per hertz at the output is always the same. You just call the amplifier a block with amplification A, and you write out the same equation, and I'll state it for you. The other thing that's good about this is, if you wanted to measure a real op-amp in a lab, which obviously you would do want to do that, it's not too difficult to get the numbers that go into this model. So it's not as if you have to sit there and measure 10 things, do some complicated mathematics, put it all into MATLAB and out pop the answer. It's actually only a couple of measurements. So it's practically useful as well. So this is our equivalent circuit for a low frequency. It's tricked. That's our equivalent circuit for a low frequency amplifier. So we've got a noise source for the source resistance, RS, and we've got a noise voltage that represents part of the amplifier noise, and a noise current that represents part of the amplifier noise. And the amplifier has got an input resistance which I call Ri. And Ri might be infinite, or it might be not infinite, a number. If Ri is much, 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 much bigger than Rs, you can usually make the assumption that Ri is pretty much infinite, Rs is pretty much zero. But not always. So we need the two noise sources, the Vn and the In, because if we just say, oh, I'll try and lump it all into Vn, or I'll try and lump it all into In, the noise result would be dependent on the size of Rs. But actually, we can choose any source that we like. It depends on the problem we're solving, and we can choose any amplifier we like. And we shouldn't have to have a number for an amplifier that depends on the source resistance, because the person who designed the amplifier doesn't know what the source resistance is, and you do, because it's your problem that's being solved. So having the In and the Vn to represent the amplifier means that the people who make the op-amp can give you these two numbers, and they don't have to worry about what your source resistance is. You will know what it is, but they don't have to know what it is. Happy with that? If we didn't have Vn and In, you just had a Vn, on the op-amp datasheet there'd be a massive list of different RSs and a different noise value for each one, and that would be unbelievably cumbersome. So Vn and In gets us out of that. Happy? So that Vn and In are all of the noise in the amplifier spooshed into two sources and put at the front. That's all. So we can find out what Vn and In are by doing some measurements and being clever about the value of Rs. We will need a true RMS meter. That's to say, if it says true RMS and you pay 20 quid for it, it's probably not that true. There's true and true. And the true RMS meters cost money. The very best ones use your signal to heat up a resistor and then measure the amount of energy that's lost from the resistor. And that's because it's the heating power that's available, the equivalent heating power that's available. And then if you had one of those, it would be called a banometer, not an RMS voltmeter. But mostly you can get an RMS voltmeter that's pretty good for a couple of £100 now. In fact, I've got one that when you turn it on, it plays a little tune that reminds me of what used to happen when you turned on a Sega Mega Drive. Any of you actually ever own a Sega Mega Drive? Just. Was it actually yours, or was it somebody else's first? Yours first. Fair enough. Right. So you've got to have an RMS voltmeter, and you need to know what its bandwidth is. But if you look in the user manual, it will tell you what the bandwidth is. If we wanted Vn, we could just say that Rs is 0. And we will do that by using a voltage source which has very low internal resistance. Certainly much, much less than Ri. And if we did that, then In would have no effect. Let's assume Ri is infinite, so Ri goes away, so there's no chance of the current leaving In flowing in Ri. Because if there was, it would develop a noise voltage across Ri, and that noise voltage would be the input of our amplifier, which means that noise voltage would be amplified, which means it would appear at the output, which would be bad news for us, because we want to take In out of the business for a bit to get Vn on its own. If I make Rs 0, this noise generator goes away, because this noise generator is 4kT times Rs. If Rs is 0, 4kT times 0, 0. So Rs disappears. Also, this point becomes connected to the ground, because we're doing superposition. We've got the three sources, worrying about this source. This resistor is 0, this source just switched off, that point to the ground. Happy with that? If you're not happy with superposition by now, you've really got to get on it, because it turns up all over the shop, in signals and systems as well as amplifiers and such. So Iron doesn't have the possibility to generate a voltage at the input by flowing through RI, because I made it infinite. And iron doesn't have the possibility of generating a noise voltage across RS, because I made it 0. RS being 0 means VNS is 0 as well, because it's the noise associated with the resistor that I just made 0. That only leaves me with VN. So now, whatever I measure here is the bit which is caused by Vn times the gain. Happy? Not happy. Plausibly happy. Well, convince yourselves with a couple of little circuits on the back of an envelope or something. So if we say that VON is only... No, it's gone. You'd think that I'd learn that that happens when I push these buttons, wouldn't you? But I don't. VON is then only caused by Vn, and we can use that expression there, gain squared times Vn squared times the bandwidth that we're measuring across all rooted gives us an output in volts per root Hz. And we can, since we measured VON, we can work backwards to get what Vn is. Now, in reality, you'll read it off a data sheet, but if you ever needed to get it for a system that you've made, and you needed to specify what the noise was, or just make sure it was below a certain level, then you might attempt this process. Now, if you've got Vn, that means you're only left with In to find, because you know what Rs is, so you know what 4kT Rs is. And you don't have to make Rs 0 anymore, now we can give it real value. And if you do give it a real value, some noise current will flow through Rs and generate a voltage. Happy with the idea of how that happens? Or no? Plausible or not? Not really. Any better? Yeah, ready it is then. I don't know what's wrong with the chalkboard really. So we had source resistance, this is VNS, that's the ground, then we got Vn, then we got In, and then our imbalance of VON. I've made Ri infinite, so it's gone away. This is Rs. In the case where Ri did exist, some noise current can flow out of the noise current generation through there and make a voltage at the input of the amplifier, and that will get amplified. And the other thing that the noise current generator can do is flow through Rs into the ground like this. It doesn't care about this source. If I only worry about this one, I switch off that one and that one, and that means they get replaced by their internal resistance. The internal resistance of this is Rs, and the internal resistance of this is 0. So that goes straight through. That essentially goes away. Let's go to the top, I suppose. We're doing that. And we're just left with that connected to ground. In flows through both of these, so it's a current sharing circuit. There are no new tricks. And the voltage that appears across Ri is In times the parallel combination of Rs and Ri. And whatever that voltage is, gets amplified. In just the same way that if I was only concerned with Vn, I'd switch off, which means that it get replaced with its internal resistance, which is infinite. That doesn't deserve a biscuit. Only the first is get a biscuit for doing that. Tell you what, actually, the first is starving to death at the minute. It'll take them a whole year to watch this video, so I'm safe. And by then, they'll be second year, so it all works beautifully. Right. So I've switched off In, so it's been replaced by infinite impedance, and I've switched off the source resistance. I've switched off the noise of the source resistance. I've still got a source resistance, but I'm calling it noiseless. And the reason I'm doing that is I only want to worry about Vn. So this is another superposition. In that case, I've got Vn, which will generate a little current, a current will flow, sorry, due to Vn and Rs, and that would be Vn plus, is that true? I'll do it this way if you prefer. Makes it easier. Yeah, like that. So the Vn that appears, oh sorry, the voltage that appears here will be whatever Vn is plus whatever the current that flows in Rs dropped is. And that's why I'm going to make Rs equal to 0 when I do this one. Because then I know that this goes away, because that's gone, goes in a straight line, so that everything that comes out of my amplifier is the gain times Vn. They are the two situations I'm heading towards by selecting my value of Rs. I'm going to have 0 in this case, and in the case where I'm worried about the noise current, it doesn't matter what I choose Rs to be, as long as it's not 0. So I make it nice and big, because then the current will flow through the big resistor and generate good voltage, give me a nice big answer. Happy? Happier. I'll take happier. Anyway, if you put in all the sources and you decide to make a big equation, the big equation that you will arrive at, assuming you've done it right, is this one here. So you've got the output noise mean squared is gain squared times noise voltage amplifier potentially divided between Ri and Rs and Ri, all squared, because we're going to have the squared answer. Voltage noise squared mean of the source resistance, also potentially divided between Ri and Rs. And the noise current, which is current shared between Ri and Rs. That's squared and that's squared as well, for the same reason, head towards the square. All times the bandwidth that we do the measurement in. So if Ri was infinite and Rs was 0, that would all collapse down to that one up there if we took roots. And if we made Ri infinite, Rs was a real value, it would collapse down in a different way, and we'd be measuring one of the partial circuits that I drew up over there. But there is, okay, if you want to just remember that, that's fine. But it would be really nice if you could rewrite it anyway, just because it would be useful eventually, possibly. If you've got designs on banking or something, it probably isn't going to be that useful, but the statistics will be unbelievably useful. Though quite why the bankers can't predict the markets are going to go down surprises me. The fact that they can't predict when they're going to be caught for cheating really surprises me. And you think they try to predict the future, that's basically their job, and that's what they use statistics for, which is why they love engineers, because we all do maths. But they don't seem to be very good at doing the predicting. Right, so if you look at one, that term are almost the same. In fact, that and that are identical. And if I factored Rs out here, they'd all be the same as each other. Not that bit, and that bit. Just this bracket, that bracket. Take Rs out here, put it there, and then that bracket, all the same. In which case, we get 2. So I just factored out, I've got an Rs squared there. Happy? Much easier to remember that for if you ask me. Now, depending on the amplifier you've got, your Ri, tell you what, I'll draw it up here again just so I've got what the point's at. Depending on your type of amplifier, Ri can be very, very large. Specifically MOSFET input amplifiers. And very large means a teraohm or thereabouts. If that's the case, you must have some Rs. Now you can never escape from the fact you've got some Rs anyway, but you've got to make sure that you know what the value is, so you define it somehow. And that means if you think it's low, but I don't know how low, I can accept an Rs of 10 ohms will not make too much difference to the noise, you'll pop 10 ohms in there just to make sure you know it's about 10 ohms. If you knew it was sort of less than an ohm before, 10 ohms plus less than an ohm, about 10 ohms. The reason you might want to do that is iron will generate, I shan't do that because I'm blind when I do, possibly myself. Iron has to flow in something, and it will be very difficult for us to work out the noise current, well, the noise voltage that appears at the output due to the noise current flowing in an RS we know nothing about, if this is far too big to be appearing in the calculation. That and that appear parallel with each other as far as this is concerned. If this is 10 to the 12 and this is quite small, the parallel combination is quite small, and the big input resistance makes no difference. Yeah or no? Good. Got one yes, that's enough to carry on. Actually, if you've got a FET input op-amp, usually when you look at the data sheet, you'll find that IN squared is unbelievably small because there isn't going to be a very significant biasing current flowing into the op-amp anyway. Now, you can't directly equate biasing currents with noise, but a lot of the time, the two go together. That's to say, up and down together. So with FET input, no biasing current, so we can expect quite a low input noise current. And actually, about 10 femtoamps per root hertz is not implausible. And that means that Vn squared, which is usually quite a lot bigger, maybe 4 nanovolts per root hertz, for example, will be the dominant noise contributor. Is there a mistake? Have you spotted a mistake? No. Alright, okay. I thought you'd seen something and I spelt it wrong. Oftentimes I do. So when you are calculating, if I had a question that said, you've got a FET input op-amp and you're going to use it in such a situation, do me some calculations to get 3 marks, you will know, James wants me to ignore the IN squared term because it's going to be quite small. Of course, if the same question was for 4 marks, you might be wondering what the extra marks for. Maybe it's for writing, I will neglect IN because I know that it's not significant in this case. Not saying that will come up or anything, just might. So, very small IN squared can be neglected. If, on the other hand, your RI is not very large, that's to say, it's not many, many, many times larger than RS, oftentimes you can't neglect it. And when I say not very large, we'll say less than 10 megaohms. But if RS can be reduced, can be removed, then equation number 1 disappears down to this one here. That one, I think that should probably say 2, but since they are actually the same expression, just one's factored, it doesn't really matter. And of course, number 3, equation number 3, at this point, we've already done the work that we needed to do to get Vn. So we know what Vn is and it's out of the picture. That's assumed. Just there. If you can't see it, which you probably can't because it's quite a large set of steps, derive it and you will see where I did it. It'll be the bit where you go, what's he done here? That. Happy with the idea of a general model for amplifiers composed of a noise source, resistance, and a Vn and an IN. And that the Vn and IN are both necessary to make our model of the amplifier valid irrespective of the value of RS. They're the key things. So now we need to talk a bit about operational amplifiers. Now what we discussed before was an amplifier and it had a gain of G and only one input. That doesn't really look like an op-amp because an op-amp's got a non-inverting and inverting input. Towards the end of this lecture, we will merge the op-amp and our simple amplifier model, and we'll make our lives very easy when we do that. But we can actually figure out some interesting things about how to optimize the noise of your circuit for an op-amp by worrying about a real op-amp with 2 inputs. So op-amps can be quite complicated. I wanted to put a smiley face, but I thought that would be a bit much. if you were here for the first 5 lectures, you'd probably agree that there's rather a lot to them, and you have to worry about many things with each circuit choice. There are not many things where you can say, I can choose this independent of everything, and it's my free choice. That doesn't often happen. Every choice that you make has some constraints, and it has some effects that you have to take into account later. It's all bound up together, which is why it's very difficult for a computer to make a design for a good analog circuit. It takes a person's sort of meandering mind to make it go. There's no right or wrong way. There are just some rules that we can apply. So op-amps can be quite complicated, and it's not, I wouldn't say practical. You can do it if you've got a long train journey and a big delay, but you wouldn't want to sit there and go, well, I've got a differential pair, so that means 2 shot noise sources, and I've got a current mirror, 2 more, and I'm going to have some sort of current source at the top, so I'll have a couple of noise resistances from the 2 resistors, and then I'm going to have a shot noise source, and on you would go. And then you've got to worry out what happens to the feedback as well, and it all gets a bit furry. Spice will do that. It just puts it all into a massive matrix and crunches the numbers for you and gives you an answer. And it'll tell you the noise output is this much at such and such a node. Brilliant. The only thing it can't tell you is the really important bit. What is the dominant cause of that noise? Because you want to make the noise as small as you can, unless you're in some very special circumstances. And if you know what the dominant source is, you can reduce the noise very easily, because the noise sources all tend to add up as the sum of the squares rooted. That was from a couple of level 10, how to combine noise sources. So if you reduce the dominant one, you're really cutting down the noise, because they'll get squared and then added. So we want to be able to say some rules about how to make the circuit better, not just have a number. Nothing wrong with having the numbers, great, but it can't tell you everything. So based on our general model of the op-amp, we will extend it to make, the general model of an amplifier, we will extend it to make a model for an op-amp, and it's that one there. So I've got a noise generator for the inverting input, current, and a noise generator for the non-inverting input, which is also a current. And I've got a noise voltage on the non-inverting input. And you might be thinking, well, what if you want to make an inverting amplifier? It's the same, and it can be shown later, although I don't actually show it, I just state it. But you ought to be able to show it by deriving that it's the same either way. So let's imagine that I wanted to make either an inverting or a non-inverting amplifier. Let's start with the non-inverting. R3 doesn't really play a part, because generally speaking you connect your source to here, and then your gain will be set by these two, R2 plus R2 over R1, R2 plus R1 over R2, yeah, that one. I have to derive it every time, I can't remember the equation. 1 plus R2 over R1, there we go. If, on the other hand, I wanted to make an inverting amplifier, I'd be hooking this point to ground, put my source here, a signal source, and my gain would be minus R2 over R1. So I could make either with this. Now I put R3 in because it generalises it, and also, if we were worried about other effects of the on the op-amp, like the amount of DC offset you get, putting in R3 can adjust your DC offset, and you might like to try and get it towards 0, although there is a bit of stuff to do with the choice of the op-amp as well. But this course doesn't contain DC offsets anymore, so let's just say R3 is there because it generalises the circuit. If you want to know about op-amp offsets, I've got some lovely notes on it, but it's not in the exam, so I have sneaking suspicion there won't be a lot of interest. Thought not. So happy with the idea that non-inverting signal source ends up here and the ground shuffles down, and inverting signal source ends up here and the ground shuffles down. Yeah? It's just a regular op-amp circuit with noise sources thrown in. If you did superposition on each one of those noise sources in turn, you would eventually arrive at equation 4, assuming you didn't make a mistake along the way, where G is the closed loop gain for a non-inverting amplifier. Even if you made an inverting amplifier, the gain that multiplies some of your noise terms will be the non-inverting gain. And if you read in a book, the noise gain of such and such an amplifier, that's what it's telling you. It says the non-inverting gain, even if you made an inverting amplifier. And then you would have a term due to IN times R3. So this is the voltage that appears because of IN thrown through R3. And then you've got a term due to the voltage that appears due to IN flowing through the parallel combination of R1, R2, R1 plus, so parallel combination of that. And then you've got a term of noise that appears due to Vn, and you have a term which appears due to the noise of the voltage noise. So this is thermal noise of the feedback resistors, of which you are in direct control because you can choose their values. And then you've got a voltage noise of resistor number 3, which may be dealing with your offsets, or maybe 0. Happy with what all the terms mean? Yeah? Or no? Okay. So, non-inverting gain is also called noise gain. Having looked at all the terms, we can draw some conclusions. Now, I didn't just sit and write these because I thought they were the best ones. These are widely believed and can be found in any textbook. So IN squared plus, which is the noise current generator at the non-inverting invert, which is what plus means, times R3, so that's the voltage that's developed across R3 by the current, noise current that flows through it, is due to the voltage across R3 flowing through IN plus. If R3 is 0, the noise goes away. So if you don't mind about your offsets, R3 is 0 is a good move, because it will get rid of some noise. If you can't reduce R3 because you need it for some reason, the best you can hope for is to look for an op-amp whose specifications say that IN is small. In other words, choose a better op-amp, where better is depending on the problem that you're trying to solve. The bias current, the noise generator, actually if you do look into offsets, the circuits are almost identical and it's the same set of analysis as well. So I do sometimes slip between them. The noise current generator at the inverting invert, which is what the minus sign means, flows, so it's current divided between R1 and R2, which is just to say they're in parallel. And you can set R1 and R2 because they give you your gain. If you go back to the diagram, we'll have R1 and R2 will be setting up the gain. Non-inverting or inverting, they still set the gain. So we're in control of those and we can take them up and down together. But if you bought an op-amp like a TL81, which is the op-amp that's in the amplifier lab from the first semester, you might have found that it can only supply about 7 or 8 milliamps. If you reduce your feedback resistors to 1 ohm and 0.1 ohm and hope for a gain of 11 or minus 10, you can't do that because 7 milliamps will flow, because that's all that can flow. You won't develop the right voltages because the resistors are too small and your op-amp will get a bit hot and then it will decide it wants to go to sleep. If you're really unlucky, the top will pop off and smoke will come out from inside. Always good fun. But that's how you learn about stuff and things. Cheers. That's what you ought to be doing, blowing stuff up. I blow up stuff all the time. Still teaches me things. Although, I must admit, as time has gone by, the stuff I blow up is now more expensive than it used to be. So I do it less regularly, because I'm more experienced. So it all works out okay in the end. Right. Same rules apply for R1 and R2 about DC offsets as they did for R3, so you've got to be careful about what you choose. Vn squared is the op-amp's noise voltage. You can't do anything about it. That's to say, you can't fiddle some resistors to make it go away or smaller. The only thing you can do is buy a different op-amp. The noise, thermal noise, due to the feedback resistors, is R1 and R2 look like they're in parallel from both of the thermal noise generators' points of view. Wow, bad English. So if I was VN2, R2 and R1 look like they're in parallel with each other from here, because that gets switched off and so does all this stuff. So they go open, that goes short, and that goes short. But if I was VN1, R1 and R2 look like they're in parallel as well. VN2 goes short, and that goes over, and that goes over, and that goes short, and that goes short. If you don't believe me, do the superposition. It'd be a good idea if you do it anyway, just so you can. Where did I get to? There. So the thermal noise of the feedback resistors, you can make those both smaller for KTR, just make R smaller, but you do run into the same problems that op-amps can only supply so much current. And it does affect your offsets. If, of course, the gain is enormous, that means your R1 will be much, much bigger than your R2 to give you the big gain. And since they're in parallel, that means the littler resistor will be the one that's significant. So that can sometimes simplify your calculations. And Vn squared 3 is the thermal noise of the resistor that's in series with the non-inverting input. And that may be there to deal with offsets, or it may not be there at all. The same constraints apply as in point 1, which is if R3 is 0 and the noise goes away, if you need R3 to deal with your offsets or something else, then you can't really adjust its value. And therefore you can't change its noise. So if you bought a regular op-amp like a TLO81, no, not like a TLO81, it's a FET input, 741s, standard op-amp, it's been around forever, that will probably have about 20 nanovolts per root hertz for VN, and total output from the op-amp noise will probably be about the same as a 24 kilo ohm resistor at room temperature. So if I said the T effective is 293 degrees, then the resistance that I'd have to have at that temperature would be about 24 kilo ohms or so. But if you can fiddle the resistor values in your circuit, you can make those numbers go down. And obviously that reduces your noise. FET input op-amps, on the other hand, very, very small input noise current, quite large input noise voltage by comparison. So if you need to get rid of 1 and 2, which is the currents flowing through resistors generating noise voltages, in my list, you can choose a FET input op-amp. Also, when you have a FET input op-amp, you can often ignore that current. So, a simplified model of the op-amp, you might be thinking this picture looks very, very similar to that picture. They are in fact subtly different, because by the time I've written this bit, I forgot I drew that earlier diagram. I drew it all again. But I should think they're very similar. Let us assume that you have designed your op-amp circuit so that it's non-inverting, and so that the thermal noise associated with your feedback resistors isn't significant anymore. You've chosen your feedback resistors carefully. They're as small as you can make them without violating any other rules to do DC conditions and so forth. The input resistance is noiseless because it's a model resistance that we've concocted to lump all the resistance inside the amplifier that looks from the input. So it doesn't have any noise. So we're down to just one VN and one IN, so we're back in the situation we were when I started talking this morning. And we have the same expression that we had when I started talking this morning, which is 5. 5 and 1 is the same, I think. So we need to make the two models go together. And we do that by making sure our resistor choices are cunning. That's all it takes. When you buy an op-amp, they don't give you IN plus and IN minus. They give you IN and the VN as well. The bit in the middle, the dark and confusing bit in the middle of the trilogy, was only there to show you, or to show generally, that choosing your feedback resistor values impacts your noise a lot. And you can, if you choose them carefully, use the same model that we use for a generic amplifier on an op-amp. If you don't choose them carefully, you have to do quite a lot more maths to get to the answer that's true. So if I was to ask a question, maybe on an exam, maybe one that's coming soon, maybe one I've already written, maybe. It could go along the lines of a particular amplifier has an input resistance of 100 kiloohms and a voltage gain of 100 volts per volt, and an equivalent input noise voltage generator, that's IN, of VN, nearly, 6 nanovolts per root hertz. Oh, there's a slash missing there. Oh, and there. Sorry. Yeah, it's per root hertz and per root hertz in both cases. So input noise voltage Vn, 6 nanovolts per root hertz. Input noise current, 0.0075 picoamps per root hertz. That's jolly small. 7.5 femtoamps per root hertz. Almost nearly nothing at all. The amplifier is fed by a noise and source resistance of a kiloohm. So that's real resistor with noise. What is the noise at the output? So you can use the standard equation. This is 6 is the same as, I don't know, 1 of them. 6 is the same as 2. Really only 2 equations, this whole lecture. And all you have to do is sub in the numbers. So the trick here is knowing what the question means, knowing what noise voltage and noise current generators are, and knowing how the circuit model looks. You can't get that diagram into your brain. By understanding it, not just by drawing it so many times you've got motor memory, you won't be able to answer the question, because the question doesn't tell you what the generators mean. That's the bit you have to know. So we're subbing all the numbers. Gain's 100 squared, which is G. Ri squared is 100 kiloohms, which is on top. Rs is a kiloohms, which is on the bottom. That's the noise voltage Vn. That's the noise of the source. That's a kiloohm. Take it from there. You've got to pick a temperature. Try and pick something sensible. Don't pick 0 Kelvin, because then I have to work out if you got it right at 0 Kelvin. And that means it takes me a lot longer to mark a script than it otherwise would. And that makes me feel vengeful. IN squared, so minus 12, and then we're going to square it. And it's got 2 significant zeros, so it's tiny now. Times a kiloohm. Kiloohm squared is a megaohm. So we've got 10 to the minus 24, and a couple of zeros on there as well, so that's 28, times 10 to the 6. That leaves us at 10 to the minus 22. And even if we root that, that'll take us back to 10 to the minus 11. Which is negligible. So I haven't even bothered to give you the answer, you just type it into a calculator and it appears. That is the style of question that you might get. Another style of question might be, I give you the op-amp model with the 2 generators derived. But that would be a bit mean. But I'm not going to tell you what's on the exam. And if you look at the tutorial problem sheets, you will find this question is like one of the ones on the problem sheets, and the question I did in Tuesday's lecture is like question 7 on the problem sheets. So it ought to be fairly clear to you where I'm taking the exam questions from. I think that's about all I can say without getting fired. Anything you want to hear from me in the last 2.5 minutes? Yes? Is there a problem class tomorrow?
Because there wasn't one last week.
What day is it tomorrow? Friday. Do our problem classes happen on Friday now? They do, right. Ah, they do, yes. No. Well, there is a problem class, but I have to lecture first years. So I won't be there, and there's nothing I can do about it, I'm afraid. But I will send someone. How's that sound? If you find the problem classes that are an awkward time, like lunchtime, on a Friday, which is a desperately awkward day, so I see all my third years and MC students, I have to lecture in the middle of it. If you're stuck, just email me. and I will arrange to see you at a time which is convenient for both of us. If, of course, you're happy to see a demonstrator, private class is fine. I will make sure someone's there. Anything else?
Who's doing the same
Hang on, there's 2 minutes. You haven't got anywhere to be.
Who's doing the
This
same
is FaceTime you're paying for. No.
Could you lump the and F together? There's nothing between like 7 sausages.
Yes. Yeah, as long as you remember to square them and then add them and root them, that's okay. Anything else you want to know? Oh yes, some people asked if they could have their raw marks from their midterms. I will have them posted on the notice board outside the student office today. I don't know how much we're going to add to all your marks to make it a bit fairer. Still haven't decided how generous I'm feeling.